Welcome back. This is Year 10 Physics. Topic Waves, Lesson 2. Make sure you've put the title, Lesson 2 date, and the title for this lesson is there ready for you. Measuring the speed of waves. Let's just check to see where this is on the spec. In Lesson 1, remember, we've looked at transverse longitudinal waves, learnt terms such as amplitude, wavelength, frequency and wave speed, and learnt how to graphically represent transverse waves. Now for Lesson 2, it's J, we'll be learning J and K on the spec. J then, learn how waves can be represented in terms of the wavelength, frequency and amplitude. Now we've already made a start on that, but we'll extend that slightly through understanding that at a constant speed, wavelength and frequency are inversely proportional. But the main part of today's lesson is to do with the speed of wave, and we'll be using two equations. Speed is distance divided by time, and wave speed is wavelength multiplied by frequency. For today we'll be completing pages 10 to 16 in your booklets. So here we go, top of page 10. The first method of measuring wave speed is using this equation, distance over time. So from the top it says, like the speed of objects such as cars and runners, wave speed can be determined by measuring the distance travelled in a given time and then calculated using the speed equation. So all you need to do is divide distance by time. Wave speed is a general property of all waves, all electromagnetic spectrum waves. Don't worry about that, we'll be learning what electromagnetic waves are later on in this topic. They all travel at exactly the same speed, the speed of light. Light is a type of electromagnetic wave, and nothing travels faster than 300 million meters per second. In standard form, that's 3 times 10 to the 8 meters per second. If light were able to travel around the world, we know it travels in straight lines, it would go around the world 8 times in 1 second. Sound waves are much slower. Sound waves travel at about 330 meters at sea level, and ultrasound travels at about 1,500 meters per second through flesh. Well, when we talk about sound, we usually use 330, sometimes up to 340 meters per second for the speed of sound in air. It does depend upon the temperature and other factors to do with the air, but generally speaking, those are the values. Seismic waves produced in an earthquake can travel as fast as 5,000 meters per second. You'd have used the equation speed equals distance over time in Year 9. You would have used it in science, possibly in geography, possibly in maths, and possibly in PE. So I'm going to do question 1 as an example, and then you're going to do question 2 and higher tier question 3. Now, as I've explained before, whenever you do a calculation, make sure you remember know. Equation, write down the equation, put in the numbers, write down the answer, and include the units. Question 1. What's it telling us? A water wave takes 20 seconds to travel 90 meters between two buoys. What is the speed of the wave? Wave speed. The first thing I'm going to do is write down the equation. That gives you your first mark by choosing the correct equation. In the exam, you'd have to choose the right equation from the inside of the exam paper. And the distance on this occasion, look, is 90 meters. It's always good to highlight the important bits of information in a question. And the time is 20 seconds. If you divided 90 by 20, you can put that in the calculator. It's the same as dividing 9 by 2, which is 4.5. So 4.5 meters per second. So question 2 and 3 are self-assessment questions. So I'd like you to do 2 there and 3 underneath. When you've completed, press play again. Remember, question 3 is for higher. Foundation and higher do question 2, only higher do question 3. So pause the video now, press play when you've completed 2 and 3. Let's now look at question 2 then. An earthquake occurs 16,000 meters or 16 kilometers away, and it takes 4 seconds for the first seismic wave to arrive. How fast is a seismic wave? How fast? How fast is another way of asking what speed. We use the equation. We don't need to rearrange this time. Good habit again, just to use a ruler there. It keeps your presentation neat. It actually helps you thinking as well. If you could see things laid out clearly, you're more likely to get the answer right. So all I'm doing is putting in the numbers. So it's like this equation. Now I'm doing the numbers. 16 divided by 4 is 4. So 16,000 divided by 4 is 4,000. So I've got the answer. I just now need the units, and that's meters per second. Question 3 for higher tier pupils reads, in a thunderstorm, the lightning is seen almost immediately. The thunder, however, travels much more slowly, 300 meters per second, 330 meters per second. If the time delay between seeing the lightning and hearing the thunder is 6 seconds, how far away is the storm? Now, how far away? That means it's asking for distance. And therefore, we need to rearrange the equation for distance. So there's a few ways of rearranging, which I showed before. Speed is distance over time. If you multiply both sides by time, then it will leave you with distance equals speed times time. Some prefer, of course, to use this method. Speed is distance over time. And you'd cover D with your thumb. You cover that with your thumb, leaving speed times time underneath. And the reason it's a higher tier question is because you need to rearrange. So the criteria to get the full marks now becomes no equation, rearrange, numbers, answer, and units. Let's do it. Speed 330, time 6. Calculator, 330 times 6 is 1980. And the units are meters. Turn over now then, please. Make sure you've marked your work correctly if you need to, in the red pen. Page 11. Speed of waves along a spring. Stretch the spring between you and a partner. Give the spring a single flick to one side to check that the wave can reach the fixed end and be reflected back in a reasonable time. Measure the extended length of the spring. On a given signal, start the wave and time it over as long as a path as possible. Now, this will be difficult for you to do at home. Of course, you need to have a Slinky spring. Many of you would have it. It's a toy you might well have. You have fun with it when it walks itself down the stairs. Although it's got that added problem that it can get twisted. We've got some in school, and in a moment I'm going to show you a quick video myself and Mr. Hancock put together to get some results to work out the speed of a Slinky spring. Two things we need to know, of course, to calculate the speed of the spring are the distance and time. So what we did was get the longest Slinky spring we could find in school and stretch it out and have some fun. We did have technical problems though with sound, so you'll have to bear with us. I've got a quick photo down here of snapshot of the video. You can just about make out where this may be in school. You can see just about here, you can see the one-way signs. I'll do it in red so it'll stand out a bit more. Right, there's the one-way sign, and it's pointing this way. All our COVID restrictions. There's the 2 meter social distancing markers on the floor, and it's difficult for you to work out, but we've actually got 12 meters between myself and Mr. Hancock, so that's 2 meters to there, 4, 6, 8, 10 and 12 all the way to Mr. Hancock. So the whole distance here is 12 meters. And what we're going to do, Mr. Hancock is going to flick the spring and a wave's going to come all the way towards me and is going to reflect all the way back. And we're going to time how long it takes. Apologies in advance. We did experience technical issues on the audio, so I've cut out the first part of the video. You can see Mr. Hancock there getting ready to create the wave. I'll press play.
Speed equals distance divided by time. The distance is from myself to Mr. Hancock and back. So here's the end of the spring, there's my hand, and you can see the end of the spring there. We're using the 2 meter social distancing measurements in the corridor. So from myself to Mr. Hancock is 2, 4, 6, 8, 10, 12 meters. So if I were to get a little flick of the spring, you can watch again. You can watch the wave come back to me from Mr. Hancock. Mr. Hancock.
Just pause it there a second. The word I should have used there is not the wave comes back to me, it's reflected back to me, and we'll be using that word in our next lesson and learning what reflection is in the next lesson. Just to summarize there, the distance between my hand and Mr. Hancock's hand is 12 meters. So the distance to go to me, to Mr. Hancock and back is 24 meters. That's the distance. And we'll be using a stopwatch to work at the time.
Well, if you could give a quick flick of the spring. That's lovely. You can see that we're going up and down. Now what we're going to do, Mr. Hancock is going to give a flick of the spring, at which point, when the wave hits my hand, I'm going to click on the stopwatch, start. It's going to go back to Mr. Hancock, back to me, covering 24 meters, and then we're going to use a stopwatch to work out the speed by measuring the time. Okay.
Just recap that again. As the wave hits my hand, I'm going to press beep on the stopwatch. I'm going to press start on the stopwatch, and you'll hear a beep, I meant to say. The wave then reflects from my hand back to Mr. Hancock's hand and reflects back to mine. I will then press stop on the stopwatch, and I'll show you the time. The time taken for the wave to travel at 24 meters, not the time on my watch. That would be silly.
Sir, if you give... Got it, right. That was 1.89 seconds. Let's do it 3 times. Repeat readings. So I'm going to reset. Whenever you're ready, sir. That was 1.95 seconds. You might be able to hear a little beep at the start and the stop. Reset. Whenever you're ready, sir. Missed it. We'll have to do that one again. So that's null and void. Whenever you're ready, sir. And that was 2.03 seconds. What we're going to do now, we're going to take an average or a mean of those 3 readings for time and divide 24 meters by the average to work out the speed of the spring.
To save time, I've written down those 3 times to work at the mean time. So these are the individual times. The first, if you remember, was 1.89, then 1.95 and 2.03. We divide by 3 because we took 3 repeat readings. If you divide the total of those times, 5.87 by 3, we get an average or mean of 1.96. And remember, by taking repeat readings gives you a reliable results. The distance travelled then was 24 meters, so we need to divide that 24 by 1.96. (24) divided by 1.96 gives us 12.2 to one decimal place. 12.2, and the units, remember, are meters per second. There's a second way of calculating wave speed, and that's using what we call the wave speed equation, which is frequency times wavelength. But to try and understand that, let's put it in context of something we already know. So we have this athlete here, the runner, and her stride length is 1.2 meters. So stride length means from her back foot to her front foot there. We'll call that 1.2 meters. And let's draw that more accurately, because importantly, the link we want you to make is this. If I draw directly up from each blue dot on the wave, we want you to think of every stride being the equivalent of a wavelength. Because the wavelength is the distance a wave travels in one cycle. That's why it's called the wavelength. And we use the symbol lambda. So 1.2 meters, in this case, the stride length is exactly that, 1.2. Now, if every second she runs this total distance from here to here, then the distance she would travel in 1 second would be 3 lots of 1.2, which would be 3.6. So her speed would be 1.2 times 3 equals 3.6 meters every second per second. Now consider the wave trace with identical number values. So the wavelength, let me just draw that again for you. The wavelength, that's from, it can be from midpoint to midpoint or peak to peak on adjacent waves. That's 1.2 meters. The frequency, that's the number of waves produced per second. And that's 3 in this case. 3, and we use the units, excuse me, hertz. H-E-R-T-Z. Hertz. So if we wanted to work out the wave speed this way, we write down the equation and we put in the values. Equation, number, answer and units. So that's going to be 3.6 meters per second. Compare and contrast. Compare and contrast. We're working out the speed of the wave 2 different ways. There we go. Now underneath here, and I'm going to highlight it as I talk through it, it says F That's frequency equals speed, wave speed divided by wavelength. That's just rearranging this equation. Frequency is wave speed over wavelength. If V is constant, that means stays the same, then we can say that frequency is inversely proportional to wavelength. Now everything that I just said there, I want you to explain in your own words, and you can rewind the recording and listen to it back. But before you do that, I want to use a bit of simulation software to make you understand that a little better, because it is an important part of physics and understanding waves, and we'll be using it more when we learn about the electromagnetic spectrum, because as mentioned earlier, you will be learning about it later, and every wave in the electromagnetic spectrum is a constant velocity of 3 times 10 to the 8, 300 million meters per second. So let's have a look at a piece of software that help you with your understanding. This is a bit of software that you can all access online. You just type in PHET Colorado, P-H-E-T Colorado. There's lots of brilliant simulations of physics, maths and other subjects, science related in there as well. Okay, now what's going on here? If I just pause this for a second. We've got an oscillation going up and down, creating the wave on this string. And at the moment we've got a frequency of 2 Hertz. Watch. If I do this in slow motion, you can see it a little bit more clearly. And if I put a timer up, and when this green particle gets to the top of the cycle, I'm going to press play, and you should see that every second, because we're in slow motion now, this green dot goes down and back up twice. In fact, I'll stop it, and when it gets to the top, I'm gonna press start and say start, and then count how many cycles are produced in 10 seconds. So start. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I should have stopped. There, it's a bit slow stopping. It was 5 seconds. So you have 10 cycles in 5 seconds. That means 10 waves are produced. Let me just pause here a second. Look at my cursor. That's the top of one wave. Peak, trough, peak. That's one cycle. The reason this particle is here is because from the last cycle, this piston has gone up and down. Now the wavelength there can be measured, and we can use a ruler to do that. If I use a ruler and just put it there, so I could do it on this one here. It's a bit easier to measure. We'll use the bottom of the ruler, so you can see 1 centimeter, 1.2, 1.4, 1.6, 1.8, 1.8 centimeters. The frequency we know is 2. and the wavelength is 1.8. Now, what if we have the frequency? If we have the frequency, let's move this over here just to show you what we're doing. So, what we're saying then is if the velocity is constant, then the frequency is inversely proportional to the wavelength. Or we could say that the wavelength is inversely proportional to the frequency. What does that mean? All that means is if you double the frequency, you halve the wavelength. Or if you halve the frequency, you double the wavelength. So what did we just have? We had a frequency of 2 Hertz. We had a wavelength of 1.8 centimeters. I want you to think now, what's going to happen if we put a frequency of 1 Hertz into that simulator? What would the wavelength become? What do you think about it? Write it down. If you're in class, tell a partner. If you're at home, just write it down. And just remember, what we do know is this. So what we're doing, let me write it the other way around. What we're doing there, we're going from 2 Hertz to 1 Hertz. So if that number on the bottom is getting less, we'd expect this to go up. So we would expect then the wavelength now to be 2 times 18 is 36, 2 times 1.8 is 3.6 centimeters. So if we go back to this piece of software, we're going to change the frequency to 1 Hertz. And by changing it to 1 Hertz, we should have a different wavelength. Let's have a look at that. And this is in slow motion, remember. I'll do it at normal speed. There we go. And I'm just going to pause it. And get the ruler. Just happen to be in the right place. So 1, 2, 3, 3.2, 3.4, 3.6. 3.6 centimeters. So that just goes to show that the relationship between frequency and wavelength is inversely proportional. You double one, the other halves. Now I can show that here again. Look what happens. Just look at the wavelength as I take the frequency. Oh, that's 0 Hertz. That's not good, is it? Look what happens now when I start to increase the frequency. Look how slow that is. Look how slow this is. 0.03 Hertz. Imagine how long that wavelength would be. We wouldn't be able to measure it on this screen. So I'm going to just take things up a little. To 0.5 Hertz. How many waves would be produced every second? Just have to think about that. Well, what you should find is that you get 2 waves a second, and we can just show that using this timer. Just count it out. So when that green dot gets to the top, I'll press play. Okay. Let's do that again. and we'll count together. We'll go up to 5 seconds and see how many waves we get in 5 seconds. 1, 2, it's 2.5. Okay, so we got 2.5 in 5 seconds. So that means we were getting half a wave, 0.5 waves per second. Before we finish it, and I'm just going to start increasing the frequency. Watch what happens to the wavelength. Higher frequency, smaller wavelength. High frequency, small wavelength. Look how close the peaks are getting together now as the frequency is increasing. And so I hope that, if you can visualize that, it gives you a good understanding of the relationship between frequency and wavelength. And again, if I take it right down, watch what happens now. Small frequency, massive, big wavelength. Oh, how low can you go? Look at that. It's off the screen. So what you do here now then, in your own words. It's no good me writing it down and you copying, because you may not learn as effectively as if you think about it, make sense of it, and write it down. I'll say it one more time. Frequency equals speed divided by wavelength. If the speed is constant, then frequency is inversely proportional to wavelength. This means if you double the frequency, you have the wavelength. Because I could have written this down here the other way around. Wavelength is inversely proportional to frequency. Press pause, complete that paragraph, and then press play. Move on then to page 13. Remember, some of you are happy in terms of rearranging, and if you're doing higher tier, you need to rearrange. For example, if you want to get F on its own, you divide both sides by lambda. That would leave you with F equals V over lambda. Or you can use this method. Where you cover one with your thumb to get the equation. We've got now 1, 2, 3, 4, 5, 6 questions. I'll do a few. Make sure that you check. Some are higher tier, some aren't. So you can see these. So 6, 5, 4, 3 are higher tier. I'm going to do question 1. Question 2 will be a self-assess, and then question 3 onwards will be a teacher assess. Get your highlighter ready. A certain sound wave has a frequency of 170 Hertz cycles per second on a wavelength of 2 meters. What's the speed of the wave? Equation, numbers, so that's 170 for F and 2 for wavelength. multiply 170 by 2, that's 340 meters per second. Question 2 is for you to do. So make sure you follow that same equation, number, answer, units, and you can't go far wrong. So press pause in a moment. When you've completed it, press play. Okay, now I'd like you to get your red pen and mark your work for question 2. What do we know? Well, we're given the speed and the frequency is 3 Hertz. Calculate the wavelength. You could use this here to get the right equation. Lambda is V over F. Wavelength is speed over frequency. The speed is 15 and the frequency is 3. That's 5 Hertz. Actually, I will just do question 3 as an example because there's slight complications in terms of we're using prefix. It shouldn't be a problem, but I'll do it nonetheless. Calculate the wavelength of the radio wave. So I've already up above rearranged for wavelength, which is speed over frequency. The speed is here, the frequency is there. You just put in the numbers. Just remember though, when you're doing the frequency, it's 96.4 times 10 to the 6, because the 10 to the 6 is that mega hertz there. Anyway, you can do it from there now, because the rest of it is straightforward. You might want to, rather than write out 300 million, it's quicker to do it that way. And you can put that into your calculator. So those questions for you to do. Which brings us on to the practical, and this is the specified practical that you need to understand for this topic. And the investigation is this. Does the depth of water in a container influence the speed of a water wave? The depth of the water is the independent variable. Remember, the independent variable is the one thing that we change. Depth of water. The speed of the water wave is our dependent variable. That's the thing we measure, the variable we measure. And we must keep everything else the same. Use numbers 1 to 6 to order the sentences correctly to provide a valid method to test this theory. Well, I'll talk through it. I'll then show you a link I'd like you to click on, which is on Study Zone, so that it's explained in a different way. Before then, you number these underneath on page 15 to get the correct method. So it's quite a straightforward experiment. You just fill a tank or tray of water, and you use a ruler to measure the depth of the water. You lift one side up, you place it back down on the desk, and the wave will go up and down and reflect off the side of the tray. Very similar to the Slinky spring going from myself to Mr. Hancock. Because we're able to measure the length of the tray, wasn't very accurate, was it? You do that again. Let's get my ruler. The length of the tray, which is this here, let's zoom in. Okay, so this is the length of the tray. By measuring that, we can work out the distance that the water wave travels. And by using a stopwatch, we can then measure the time it takes to travel that distance. Before you do this then, we're going to watch a video and I'll show you where that video is now. I'll show you now the link I'd like you to go to watch a fuller explanation of this experiment. So study zone page, and for this lesson, so you should be on the right page already, and then you just click on this link here, Wave Speed Practical Video Link. Click on that and there'll be a 3-4 minute explanation of the experiment. Likewise, what I've copied in here is from the specification, and it's got the full method here for you, and you can pause the video on there, which gives you another description of the experiment and help you answer the activity you're going to do next. You will be plotting a graph in a moment. There's the risk assessment. I won't go through all of that. And how you could take a range of different depths of water, take repeat readings and work out the mean speed. But we've already taken some readings in an example and a question for you to try later. So just number those boxes on the left hand side and press pause now, and when you've numbered those boxes, press play to compare. I've completed it there, so check against that. I won't read through each one, but one thing I will highlight is the range and the intervals, because we've got these values down here of the independent variable, the different depths. The range, remember, is from the highest to lowest values. So that's 5 take away 1, giving you 4 centimeters. And the interval is the gaps between successive depths. So 1 centimeter, 2, 3, 4, 5, all 1 centimeter. Right, turn on to page 16, please. This is a past exam question, but also an opportunity for you to plot a graph of the independent variable depth of water against the wave speed. And what you can see before you start plotting is that as the depth of water increases, the wave speed increases. Then the rest of the questions underneath are relating to the graph. So I'd like you then to complete part A and part B. This will be a self-assessed question. So what you need to do is press pause now And when you've completed A and B, press play again. I've just plotted the points underneath. Because depth is the independent variable, that needs to go on the horizontal axis, and wave speed on the vertical. You should have a curve of best fit. When you draw your curve of best fit, I'll do it in a different colour. It hasn't got to necessarily go through each one of those points, but you're trying to get a smooth curve. It's not the best one. There's a little bit bumpy at points on the way through. That's a little better. Now, again, that's slightly below the point here. That's slightly below, but just do your best when you draw that curve, and it might help if you just rotate the paper that you're working on, so you can use your elbow as a pivot and your arm works almost like a compass. Okay, anyway, that's what you need to do for part A. 2. Describe how the wave speed changes with the depth of the water. Obviously you'll be answering here, but I've copied over to the side so that you can read it properly. Describe how the wave speed changes with the depth of water. This is looking for, you're going to give an explanation. How does one thing affect the other? How does wave speed, how is it affected by the depth of water? Well, you can see the deeper the water, the faster the wave. You could embellish or improve the answer by taking some figures. Because you could say that as the wave speed increases from 1.5 to 4, the speed goes from 3.8 to 6. But the main part of the answer you need to include is, and I'm not going to write these down, these are for you to write down, as the depth of water increases, the wave speed increases. B. Use your graph to answer the following questions. Water waves produced by a wave machine in a swimming pool has a wavelength of 8.1 meters, where the depth of the water is 3. So it's given us that. Use a suitable equation and calculate the frequency of these waves in the pool. Now, to work out the frequency, we use the equation V over lambda, speed over wavelength. We've been given a wavelength of 8.1, so we can write that in, but we don't know the speed yet. But what we do know is the depth of the water. And if we know the depth of the water by using the graph, we can work out the speed. Even though, of course, if we look at this table, it doesn't tell us what the speed is when the depth of the water is 3. It tells us what there is at 2.5. That's 4.9 meters per second. It tells us 3.5, 5.7 meters per second. So we know the speed is going to be in between 4.9 and 5.7. That is why we use curves or lines of best fit. Now if we look at this graph, we can use extraction lines. So if I'll use a different colour, if I just choose red, find the ruler and go up from 3 as the depth of the water, there. And then you can see if I go across from where it hits the curve of best fit, it's here. Let's work that out as a speed. Well, this line here is 4, this is 6. We've got 2 divided by 5 equal divisions. 1, 2, 3, 4, 5. 2 divided by 5 is 2/5 as a fraction, or 0.4 meters per second as a decimal. So we've got 4.4, 4.8, and that would be 5.2. 5.2 meters per second. All we do now is take that value of speed and we put it in the equation, if I can find it. It's hiding from me. Where have you gone? Where have you gone? There it is. So I write 5.2 in here and then just use the calculator. Oh, not sure what's happening there. 5.2 divided by 8.1. I think that was right. Say 0.64. Don't fully believe it, so I'm going to go back to the usual mode. Let's try that again. 5.2 divided by 8.1. Where have you gone? 8.1. There we go. Yeah. 0.64 to 2 decimal places. 0.64. And remember, of course, the units. The units of frequency are hertz. So that's B part 1. B part 2 requires a bit more thinking because you've got to make 2 connections. The first connection, I'll just read it first of all because it's quite a tricky question. As the waves travel from A to B in the pool, the frequency remains constant. Explain what happens to the wavelength. Well, what we can see as we're going from A to B, left to right, the depth decreases. This is a way to think about it. You're looking for relationships between different variables. And we know from this graph that when the depth decreases, the wave speed decreases. So the speed decreases. But the question's asking, what happens to the wavelength? Well, using this equation, what we can say is lambda, that's a wavelength, equals the speed divided by the frequency. But because the frequency is a constant, so look at all these jumps we're making. I'm going to put arrows in between the jumps. Because the depth is low, the speed is low. Then we've got this relationship between the wavelength and the frequency because the wavelength and the speed. What we can say is this: the two are directly proportional to each other because the frequency is a constant. Meaning that if the speed goes up, the wavelength goes up, and vice versa. If the speed goes down, the wavelength goes down. And that's what it's asking us to do. Explain what happens to the wavelength. Now, if you said the wavelength decreases, you get a mark. But to get the full 2 marks, you need to explain why it decreases. So it's good in the answer to first of all state what you think is going to happen. And what you think is going to happen is the wavelength is going to decrease. So I'll do B part 2 just here. The wavelength will decrease from A to B. Because, as you've always been taught, the because is used to give the reason. Because the depth decreases from A to B, causing the speed to decrease that in turn decreases the wavelength. Now, this phenomenon of the depth of water affecting the speed of the wave explains why waves break as they approach the shore on a beach. And that's why we have what's called a surf zone close to the beach. And what the surfers try to do, they try to catch these waves. I'm not going to attempt to draw a surfboard there, don't worry. They catch these waves and surf in. Now, the reason they break is because the front of the wave here, that I'm putting that big red splodge on, is slower than the back of the wave here. So the back catches up with the front. And then, as it says underneath, the back of the wave moves faster than the front, the wave becomes too high and breaks. Useful to think about that when you see waves break. That is the end of lesson 2. See you next time. Bye.